The question sounds like something from a movie. A villain in a hollowed out volcano, a giant laser, a button that splits the earth open. Can we actually trigger an earthquake on purpose? It's a huge question, and the answer isn't a simple yes or no. It's more like yes, but not in the way you think. And no, definitely not in the way you think. Let's get the basics straight first. What is an earthquake? Imagine you're trying to slide two big, heavy, rough wooden planks past each other. They don't slide smoothly, they get stuck, the edges snag on each other, you keep pushing. The pressure builds and builds. The wood starts to bend a little under the strain. And then, all at once, with a loud crack, it slips. All that stored up energy is released in a sudden, violent jerk. That's an earthquake. The wooden planks are tectonic plates, giant pieces of the Earth's crust. They are always moving, but they get stuck on each other at the edges, which we call fault lines. The pressure, the strain, builds up for years, decades, sometimes centuries. When it finally lets go, the ground shakes. The energy released in a big earthquake is almost impossible to imagine. A magnitude 7 quake releases as much energy as thousands of atomic bombs. A magnitude 8 is about 30 times more powerful than that. A magnitude 9 is another 30 times more powerful still. We are talking about forces that shape planets. So when we ask if we can trigger one, we are really asking two things. Can we cause the ground to shake? And can we force one of these massive continent-sized plates to slip when we want it to? The answer to the first question is a definite yes. We do it all the time, we just do it by accident. This is called induced seismicity. It's a fancy term for earthquakes caused by human activity. For a long time, we didn't even realize we were doing it, but the evidence is now overwhelming. One of the biggest culprits is the oil and gas industry, specifically a process called wastewater injection. When companies drill for oil and natural gas, a lot of salty, chemical-filled water comes up with it. You can't just dump this stuff in a river, so the standard practice is to pump it back deep underground into porous rock formations. Think about what's happening there. You're forcing billions of gallons of liquid into the ground at very high pressure. This liquid seeps into the cracks and fissures in the rock deep down. It can even reach small, ancient fault lines that have been quiet for millions of years. The water acts like a lubricant. It gets between the two sides of the fault, pushing them apart just a tiny bit and reducing the friction that holds them in place. If there was already some stress on that fault, this little nudge can be enough to make it slip. The state of Oklahoma is the textbook example of this. For most of its history, Oklahoma had very few earthquakes. Then, around 2009, things started to change. The number of quakes began to skyrocket. Not just tiny tremors, but magnitude 3, 4, and even 5 quakes. Enough to crack walls, break windows, and scare the hell out of people. Scientists studied it and found a direct link. The areas with the most earthquakes were the same areas with the most wastewater injection wells. The industry pumped huge volumes of water underground, and the ground started shaking. When regulations were put in place to reduce the amount of water being injected, the number of earthquakes started to go down. It was a clear, if unintentional, experiment. We proved that if you pump enough liquid into the right spot, you can wake up sleeping faults. Another method is hydraulic fracturing, or fracking. This is related to wastewater injection, but it's a different process. To get natural gas out of shale rock, you have to crack the rock open. Fracking involves pumping a mix of water, sand, and chemicals down a well at immense pressure. This pressure fractures the rock, releasing the trapped gas. The act of fracturing the rock itself creates tiny seismic events, micro-earthquakes. They are almost always too small for anyone to feel, but sometimes the fracking process can hit a pre-existing fault. The high-pressure fluid can do the same thing as wastewater injection, lubricate the fault, and cause it to slip. This is less common than with wastewater, but it does happen. So we can trigger small to medium-sized earthquakes by pumping fluid underground. What else? Building giant dams can do it too. When we build a huge dam, we create a massive artificial lake behind it. That water is incredibly heavy. We're talking billions of tons of weight all concentrated in one area where that weight didn't exist before. This new weight pushes down on the Earth's crust. It can change the stresses on the rock underneath and, you guessed it, can sometimes trigger earthquakes. This is called reservoir-induced seismicity. One of the most famous and debated cases is the 2008 Sichuan earthquake in China. It was a massive, devastating magnitude 7.9 quake that killed nearly 70,000 people. Just a few miles from the epicenter was the Zipingpu Dam, a huge dam that had been filled only a few years earlier. Some scientists believe the immense weight of the water in the reservoir and the way the water seeped into faults below was the final straw that triggered the catastrophic quake. This is not proven. Many other scientists disagree, saying the quake would have happened anyway. But it's a terrifying possibility. The idea that a piece of our own engineering could have contributed to such a disaster is sobering. Mining is another one. When we dig deep into the earth to pull out coal or ore, we are removing millions of tons of rock. This changes the stress patterns in the surrounding ground. Sometimes this can lead to what are called rock bursts, which are basically small, man-made earthquakes deep in a mine. They can be violent enough to kill miners and destroy equipment. So, yes, we can and do trigger earthquakes. But notice a pattern here. The quakes are almost always relatively small. They are happening in specific places where our activities are lubricating old faults or changing local stresses. We are not causing the San Andreas Fault to rupture, we are just prodding and poking the crust in very specific, localized ways. And most importantly, we are not doing it on purpose. We are doing it as a side effect of trying to get something else, like oil, water, or minerals. This brings us to the second bigger question. Could we use this knowledge to trigger a big earthquake on purpose? Could we weaponize an earthquake? Or could we use it for good, to release pressure on a fault line before it gets too dangerous? Let's start with the villain scenario. Imagine a country wants to devastate an enemy's city. Could they sneak in, drill a deep well, and pump water into a nearby fault to set it off? The problem is control, or the complete lack of it. Let's go back to the Oklahoma example. They weren't trying to cause earthquakes, it just happened, and it wasn't one injection well causing one quake. It was thousands of wells operating over years, creating a complex, widespread change in pressure underground. This led to a swarm of earthquakes over a huge area at unpredictable times. If you wanted to trigger a specific fault at a specific time, you would need to know things we simply don't know. You would need a perfect map of the fault miles underground. You would need to know exactly how much stress it's currently under. Is it right on the edge of slipping, or does it need a huge push? You'd need to know exactly how the rock will react to the fluid you pump in. Will it seep through evenly, or will it find one fast channel and go somewhere unexpected? It's like trying to start an avalanche by throwing a single snowball. You might get lucky. If the snowpack is perfectly unstable and you hit just the right spot, maybe you'll set it off. But more likely, your snowball will just disappear. Or maybe you'll start a tiny slide that stops after 10 feet. Or maybe you'll trigger the big one, but a week later, after you've already gone home. It is not a reliable weapon. You have no idea what will happen. You could spend billions of dollars, drill a super deep well, pump a lake's worth of water down there, and nothing happens. Or you could cause a magnitude 4 quake that just breaks some windows. Or, and this is the really scary part, you could accidentally trigger the magnitude 8 monster you were hoping for, but before you're ready, or in a way that affects your own side. Geology is messy. It's not a precise machine. It's a chaotic system with a million variables. Trying to control it with our current understanding would be like a toddler trying to perform brain surgery with a crayon. But what about a bigger hammer? What about the one thing humans have created that rivals the forces of nature? A nuclear bomb. This is the classic doomsday scenario. Detonate a nuke on a major fault line, like the San Andreas, and trigger the big one. This has been studied a lot, especially during the Cold War. Both the US and the Soviet Union set off hundreds of underground nuclear explosions for testing. And they monitored the seismic effects very, very closely, partly because that's how you detect other countries' secret tests. Here's what they found. An underground nuclear explosion does create an earthquake of a sort. It creates a massive shock wave that travels through the Earth. A big one, a megaton bomb, can create seismic waves equivalent to a magnitude 6 or even 7 earthquake. So if you detonate a nuke under a city, the ground shaking alone would be incredibly destructive, on top of everything else. But triggering a natural earthquake is a different story. Remember how an earthquake works. It's the release of strain that's already stored in the rock along hundreds of square miles of a fault plane. A nuclear bomb is a point source. It releases all its energy in one tiny spot. The energy radiates outwards in all directions. It doesn't push one side of the fault one way and the other side the other way. It's an explosion, not a slip. The energy from the bomb does travel, and if it hits a fault that is right on the absolute hairy edge of slipping, it's conceivable that the shaking could be the final nudge. It could be the shout that triggers the avalanche. During the decades of nuclear testing, scientists looked for this. Did a big test in Nevada trigger a rash of earthquakes in California? The answer was no. The test did cause some very small localized adjustments and tiny tremors on faults very close to the test site. But there is no evidence that a nuclear test has ever triggered a major distant earthquake. The scale is just wrong. Even the biggest nuclear bomb we've ever built, the Tsar Bomba, had a yield of 50 megatons. The energy released by the 2004 Sumatra earthquake, magnitude 9.1, was equivalent to over a million of those bombs. Our biggest weapon is a firecracker compared to the power locked inside the planet's crust. Using a nuke to trigger a major earthquake is like trying to knock over a skyscraper by hitting it with a car. You'll do a lot of damage to the ground floor, but you're not going to make the whole thing collapse. The energy just isn't big enough or applied in the right way. So the weapon idea seems like a bust. It's too unpredictable if you use fluids and not powerful enough if you use bombs. But what about the other idea, the good idea? Could we use this to prevent a disaster? The concept is called fault lubrication or active seismic control. The idea is that if a fault like the San Andreas is building up stress for a massive magnitude 8 quake, maybe we could release that stress gently. Or we could drill into the fault and pump in water very carefully to trigger a series of small, harmless magnitude 3 or 4 quakes. We would let the fault creep along slowly and safely instead of letting it build up tension for 100 years and release it all at once. We would be taming the earthquake, turning a monster into a series of manageable tremors. It is, in theory, a beautiful idea, and it has been tried, sort of. Back in the 1960s, the US Army had a site near Denver, Colorado called the Rocky Mountain Arsenal. They were producing chemical weapons and needed to dispose of the toxic wastewater. So they drilled a well 2 miles deep and started pumping the waste down. Soon after, Denver, a place not known for earthquakes, started having them. A lot of them. Scientists, led by a geologist named David Evans, made the connection. They convinced the army to stop pumping. When the pumping stopped, the earthquakes eventually did too. It was one of the first and clearest demonstrations of induced seismicity. This case showed that the principle works. You can turn a fault on and off, in a way, by adding or removing fluid pressure. So, why aren't we doing this on the San Andreas Fault? Because the Rocky Mountain Arsenal experiment also showed how terrifyingly dangerous this is. The Army wasn't trying to cause earthquakes, and they were happening all over the place, with magnitudes up to 5.5. It was completely uncontrolled. Now imagine trying that on the San Andreas Fault, which runs right next to Los Angeles, a city of 18 million people. The stakes are impossibly high. Let's say you get a committee of the world's best geologists together. They pick a spot, they drill their well, they start pumping water ever so slowly. They're aiming to create a nice, gentle magnitude 3 tremor, but their calculations are off by a tiny fraction. The stress on the fault was slightly higher than they thought. The rock is slightly more permeable than they predicted. And their gentle nudge isn't so gentle. Instead of a harmless tremor, they trigger the big one. The magnitude 7.8 monster that everyone has been dreading, they have just destroyed Los Angeles. They have killed tens of thousands of people and caused trillions of dollars in damage. Who is responsible? The scientists, the government that funded them. It's a legal and ethical nightmare of a scale that has never been seen before. No one, absolutely no one, wants to be the person who had their hand on the valve when the big one hit. The problem is that we don't know enough. Our understanding of the physics deep within a fault zone is still rudimentary. We have models and theories, but we can't see what's going on down there. We are flying blind. To think we can precisely control these immense forces is hubris of the highest order. It's like a caveman finding a modern car. He might figure out that the big pedal makes it go, but he has no idea how fast or how to steer or how to stop. And he's pointing it straight at a cliff. There's also the sheer scale of the engineering. The San Andreas Fault is 800 miles long and goes at least 10 miles deep. It's not one clean crack. It's a whole zone of crushed and broken rock. To influence the entire fault, you wouldn't need one well. You'd need thousands, you'd need a plumbing system on a continental scale, pumping unimaginable amounts of water, all perfectly synchronized. The cost would be astronomical, and for what? For a project that has a very real chance of backfiring and causing the exact catastrophe it was designed to prevent. So where does that leave us? We can trigger earthquakes, we do it every day by pumping fluids underground for industrial purposes. This causes mostly small quakes, but sometimes moderate ones that can do real damage. But this is an accidental side effect, and it's a messy, unpredictable business. We probably cannot trigger a great earthquake, a magnitude 8 or 9, on purpose. A nuclear bomb, our most powerful tool, is a pinprick compared to the energy already stored in the crust. Its energy is explosive and radiates in all directions, which is the wrong kind of force to cause a fault to slip over a large area. It's the wrong tool for the job, and we absolutely should not try to use our ability to trigger small quakes to try and control a major fault. The risk is infinite. Our understanding is infantile. The consequences of getting it wrong are apocalyptic. It's a Pandora's box we are not smart enough to open. The dream of controlling the earth, of taming its fury, is a powerful one. It's a very human desire to want to command the forces of nature that threaten us. But the reality is that the planet is just too big, too powerful, and too complex. The energy scales are beyond our comprehension. We are ants living on the back of a sleeping giant. We can sometimes annoy it enough to make it twitch, but we cannot tell it when to wake up or what to do when it does. The most practical and wisest approach isn't to try to control earthquakes, it's to learn to live with them. It's to study them, to understand them better, so we can try to forecast where they might happen. It's to build better buildings that can withstand the shaking. It's to have smarter early warning systems that can give people a few precious seconds of notice. It's to prepare our cities and our communities for the day the ground inevitably starts to shake. Controlling the planet is a fantasy. Respecting it and adapting to it is survival. The power to trigger an earthquake on purpose is, for now and for the foreseeable future, beyond our grasp. And given the potential consequences, that is probably a very, very good thing.